All right, so the fourth major concept that we're going to set up in 299, we talked about electric forces, electric fields, electric potential energy, and now we're going to come back and talk about electric potential. And we're going to set up electric potential by thinking about what we talked about with the electric field. We said there's something called the electric force that is an interaction between two charges. But if we divide out the impact of one of those charges, we're left with the electric field, which tells us how some source charge influences the space around it. So the force depends on both a source charge and a test charge. The field only depends on the source charge. So the idea is that we take the field is created by a source charge, and then we probe it with a test charge by seeing how it's influenced by an electric force. We're going to set up the same sort of definition for electric potential. You guys talked in class about the electric potential energy, the change in the electric potential energy, and again, that depended on two charges. And so what we're going to do is we're going to divide out the impact of the test charge and be left with the electric potential. So in the same way, the potential energy depends on both the source charge and the test charge. But the potential depends only on the source charge. And one of the things to be explicit about right up front: potential, change in potential, potential difference, voltage, those are all ways of saying the same thing. Potential energy, on the other hand, is a very different thing. So once you tack energy on the end, you're talking about something different. It requires two charges. The potential only depends on the source charge, and again is telling you about how that source charge influences the space around it. The units for potential, well, if we think about our equation, the units for potential are going to be given by the units of potential energy divided by the units of charge. So the units of potential energy are joules, the units of charge are coulombs. So one way to think about the unit is joules per coulomb. Another way to think about it is, well, that's just given another name called the volt. And so this is part of why we will often refer to the potential as the voltage, because we're basically playing off of that unit. Now, you defined the change in the potential energy in terms of a work done by a conservative force, and so you had negative some integral from an initial position to a final position of the dot product between the electric force and your infinitesimal little steps dr as you moved from where you started to where you finished up, as you moved your charge around in space. And all we're doing is saying we're just going to divide out the influence of the charge that you're moving around. And so again, this gives us force divided by charge. That's the electric field. So the change in the potential is given by negative the integral from some initial position to some final position of the electric field dotted in with your tiny little steps dr. And so again, what this is telling you about is it's telling you in some sense about how you're moving either with or against the electric field as you move around some source charge. So you set up this equation in class that said the change in the electric potential energy due to point charges can be calculated this way. So as you have 2 point charges Q1 and Q2, and you start to move them around relative to each other, how you're changing the potential energy is given by this equation. So K, Q1, Q2 over this term in parentheses, which is 1 over the final distance between the charges minus 1 over the initial distance between the charges. So thinking about our definition, basically we get the change in potential due to a point charge by taking this equation for the change in potential energy due to point charges and dividing out one of those charges. So all we're going to do is, instead of calling it Q1 and 2Q, we're going to rename these Q source and Q test. And you see that Q test, that test charge, cancels right out. And so I'm left with an expression that says, as you move around in the space around some source charge, how the potential is changing is given by this equation. So in terms of this equation, well, if we think about, now this is your initial distance. How far away are you from the source charge? This is at the end, your final point, how far away are you from the source charge? And if you've moved away from the source charge so that your final distance is larger than your initial distance, then this quantity within the brackets is actually negative. You're taking 1 over something big minus 1 over something small. That's going to give you something that's negative. And so whether or not the change in potential is negative or positive, K is just a positive constant. This term, as we move away, is negative. So whether our delta V term is negative is going to depend on the sign of the source charge. So if we have a positive charge, positive K, positive source charge, negative term in parentheses, then what that shows us is that as we move away from positive point charges, we actually decrease the electric potential. As we move towards positive point charges, we increase the electric potential. If I flip it around so that QS is also negative, so now I've got positive K times negative Q times this negative value within parentheses, if I move away, that tells me that moving away from a negative point charge increases the electric potential. If I move towards a negative point charge, it decreases the electric potential. So in some sense, the easiest way to think about this is that positive charges sit at the top of a hill. And so as you move away from a positive charge, you're moving downhill in either direction. Negative charges sit at the bottom of a well. And as you move away from negative charges, you actually are in the process of climbing back up the well. And that's all this statement's telling us. So moving away from a negative charge increases the electric potential. So if I think about, say, this charge here, and think about the electric field that it generates out at this point P, well, the electric field, if it points towards my source charge, then this source charge must be negative. So if I want to think about what would happen if I released a test charge here, well, the first thing that occurs to me is, well, that's going to depend on what the sign of the test charge is. So if I put a positive charge here at point P and let it go, it would obviously be attracted to that negative source charge, and it would move to the left. If I put a negative test charge here at point B, it would be repelled by this negative source charge, and it would move off to the right. Either way, regardless of what point charge I put there, when I let it go, it's going to move to decrease its potential energy. So if I think about this equation, and this is just taking our definition for the change in potential and rearranging it, as soon as I let something go, I know that if it's given the chance, it's going to make this term negative. It's going to decrease its potential energy if it can. So when I think about what's going on the right-hand side, whether or not this is negative, again, depends on the interplay of the charge and the change in potential. So if my charge is positive, that means that positive charges, this would be positive. I need this term to be negative, so I've got to decrease the potential energy, which tells me that positive charges will always move from high potential to low potential if you let them go. This means that a positive charge will decrease its potential energy by running downhill. Right? Go from high potential to low potential. If this is a negative charge, on the other hand, so the Q is negative, this side's negative, the Q's already taken care of this side being negative, which means that my change in potential will now be positive. So negative charges actually increase their potential when you let them go. They go from low potential to high potential. So negative charges decrease their potential energy by running uphill. So just to see the derivation for, again, where we get the change in potential due to a point charge. So as you move around in space around a point charge, here again is my definition. I need to think about the electric field generated by this point charge, and I need to think about how I'm moving around in space. Since this is a point charge, I know it's going to give me an electric field that has a magnitude of k q over r squared. I need to take care of the signs in my dot product. So that's where this other negative sign comes from. And now when I do the integral, I know that I'm going to get the integral of 1 over r squared dr just gives me negative 1 over r, but when I take care of all those signs correctly, what I end up with is that the change in potential is given by, again, k times my source charge times this expression 1 over the final distance from my source charge to the point where I end up minus 1 over the initial distance. So how far away was I when I started? How far away was I at the end? So exactly the same equation we got by dividing that test charge impact out of the change in potential energy. Now, again, everything we've done up until now is focused on the change in potential, or the change in potential energy. And that's because if you want to talk about the potential, well, really what you mean is the potential or the potential energy relative to some 0 point. So when we say the potential energy, what we really mean is the potential energy relative to the point where the potential energy equals 0. So for your point charges, you said I'm going to let the potential energy equal 0 when they're infinitely far apart. So that gives us this equation that says the potential energy relative to the 0 point at infinity is going to be given by K, Q1, Q2 over R. Q1 and Q2 are my charges. R is the distance between my charges. Well, we've got to play exactly the same game with the potential. So to talk about the potential, again, we must have a 0 point. And we're going to do the same thing. We're going to say that the 0 point for the potential for a point charge, it's 0 at infinity. And so when we go back and sort of rearrange our equation now, we get an equation for the electric potential, which really again means the electric potential relative to the 0 point when you're infinitely far away from the point, from the charge, is given by KQ over R. Q again is the charge creating your field. R is the distance from your charge to point P. So a couple important things to highlight about this equation. One is that it can be positive because you can have a positive charge. It can be negative because Q can be a negative charge, or it can be 0 because you're infinitely far away. So if we're thinking about the potential due to a single point charge, this can take on any value you want. It can be positive, it can be negative, it can be 0, depending on what choice you've made about the source charge. 2, notice that we don't take the absolute value in this equation. We've dealt with four quantities so far: the electric force, electric field, electric potential energy, and electric potential. And for the electric force and electric field, our equation had the absolute value of Q because we were calculating the magnitude of a vector. For the electric potential and electric potential energy, those equations don't have an absolute value. So we just plug in Q with its sign as it's given. The potential depends on one charge, like the electric field. So again, of our 4 quantities at this point, 2 of them, potential and electric field, only depend on the source charge and are telling you about what's going on as you move around in space around your source charge. The force and the potential energy are telling you about an interaction between 2 charges. So I need 2 charges for the potential energy. I only need 1 charge for the potential. Potential is a scalar, not a vector. So the nice thing is that when we have to deal with multiple contributions to the potential energy, this is a scalar equation, so we're going to add it like it's a scalar equation, which means we don't have to do things that we would do for a vector addition problem. I don't have to worry about picking a coordinate system, breaking my vectors up into components, making sure I keep my x and y component equations separate. We just need to add these as numbers. Next is that R is defined to be a positive distance. So one common mistake that students will make is, let's say I've got my source charge sitting at the origin, and I'm interested in a point P that's off in some negative position. And students will often want to plug in the negative position rather than the positive distance between point P and the charge. So make sure you remember that you always want to plug in a positive value for R the way this equation is set up. And then again, we've got 4 equations. We've said 2 of them depend on 1 Q, 2 of them depend on 2 Qs. But the other thing is that's different between these equations is the potential, like the potential energy, is 1 over R. The force and field equations are 1 over R squared. So just make sure that you've got the right exponent in your denominator based on whether you're calculating potential or potential energy on the one hand, 1 over R, or force or field magnitude on the other, and that's 1 over R squared. So if we do have multiple charges, so I need to think about the contribution to the potential at point P from 2 charges Q1 and Q2. Well, the nice thing about the potential being a scalar is that this is just a simple addition. So I just add up the contribution to the electric potential from charge 1 at point P plus the contribution to the electric potential from charge 2 at point P. So this is going to give me one term, KQ1 over R1, plus a second term, KQ2 over R2. And so I just add these up as scalars if I have multiple point charges.